Thank you so much, Professor Pavitra. So, uh, okay. So, like I was mentioning, right, that means that there are these three different V's which are very crucial. And you'll look at you'll face all these V's when you move to a company where you'll notice that there's huge amount of data getting produced, and this data needs to be stored in a proper, holistic way. And that's why we have a lot of things like data warehouse and data lakes where we basically feed all the structured and unstructured data so that we get one unified view. And in the third part, which is the velocity, is when how do you basically manage these real-time services which are running, right? That means how do you manage inferencing at almost real time, right? Because today any application that we use, we will notice that all of them uses some form of machine learning functionality, right? So let me give a very quick example. Say if I want to use an assistant like Google Assistant, right, or probably Siri or even Cortana, you see that if it starts replying to you after a couple of minutes or probably takes 20, 30, 40 seconds to reply, obviously you as a user will not be very happy in using that service, right? Hence, trying to build a pipeline which is highly efficient, it comes under certain seconds of SLA, and you're able to produce the insight within that particular point of time becomes extremely crucial, because today the data is moving at a very fast speed across all these different infrastructure that we have, right from our mobile phones to our laptops. And we have become accustomed to using these things without any kind of a delay, right? So again, it also becomes a huge engineering problem in itself to serve these real-time requests and to get the least latency as possible, right? So with that, let me now move to some of the other core components of the data science process. So generally, to build, whenever you are trying to solve a data science problem, you need to first break this into smaller problem statements, right? And again, this is how even GPU generally does it. That means it tries to break the entire problem statement into smaller chunks of sub processes. So here, as you can see, there are a total of 6 paradigms which are super important. First is classifying the problem statement, right? Generally, we see that people just go ahead, take the data, apply the algorithm, and say that, hey, my algorithm is giving me this number of or these are my metrics, right? I'm getting this is my mean square error, or say if I'm using any other metrics like AOC or ROC, we just code those numbers, right? But what is really important is the fact is to formulate any business problem into a proper data science problem statement. That means how do you link a business problem with the corresponding data science problem statements, right? That means how do you basically try to address that business question? That means do you need to first explore the data, right? Explore the data and get some insights, or do you want to do something like a predictive task, right? So again, we need to be extremely mindful of what is it that we are trying to do every time. Just having these machine learning models will not be enough. You will need to do exploratory data analytics analysis, right, which is a super critical and important step in classifying the problem statement itself, right? Because without doing this, right, it becomes very difficult for you to understand that how do I want to formulate this problem statement, and if there is some predictive capability that I need, what kind of a predictive capability can I get based on the data that I have, right? So say for example, I have large volume or large corpus of data which is not labeled, right? In that point of time, I will not be able to formulate a supervised learning problem statement, right? In that case, I would either have to go for self-supervised or probably semi-supervised or even unsupervised in that matter, right? If I have less amount of data, or say out of 1 lakh samples, if I only have say 5 or 6,000, I can essentially look at the other methodologies as well, right? So you need to be very mindful based on what data is available and what kind of a problem statement that you're trying to solve. So you need to explore the business problem and also the data which is available to you at that point of time. Now, the second step is that once you have identified that, hey, to solve this particular business problem, I will need, some data from the database, which could be a tabular data with rows and columns, and probably some unstructured data as well. And the best example for this is, today we are trying to build these deep learning systems where we want to essentially, or try to build these ML systems rather that can essentially detect, cancer just by looking at the images. But most of the times, only images as an input modality will not be sufficient, right? You will have to take a mix of, structured data, which might have more pointers, right, with respect to your health related information like BMI and other aspects, right? I'm just taking a very vague example here, right? Or other physical attributes along with the unstructured data and combine these two modalities to do your modeling, right? Just one modality might not be enough for trying to solve that problem in the right way, right? Because there are also issues with respect to explainability that you as a person who has developed the system needs to provide to the end user. So choosing the right data sets, choosing, when do you need structured data, when do you need unstructured data, and when do you need the combination of those, and acquiring these data from the right sources is the next important step, which we also sometimes refer it as data engineering. The third step is obviously, whenever you get this data, right, it will also have a lot of columns or feature set which might not be of relevance for solving that business problem. Hence, what you'll have to do is you'll have to probably go through a series of transformation, normalization, and cleaning to get the data in the right structure, right, so that it is ready to be used or to be consumed by these algorithms, right? So say for example, if I have a data where there are certain, feature sets which are missing, right, certain values in the feature set which are missing, at that point of time you'll obviously require to apply some kind of techniques to handle those missing values, right? So that is just one example as such, but the whole point that I'm trying to make here is that you will have to go through a series of transformation, normalization, and cleaning before we feed that data to the machine learning algorithm, right? Because as we know that, right, if we put garbage inside a machine learning algorithm, obviously the output of the algorithm will also be garbage. So you need to be very mindful of what feature sets that you are choosing based on the problem statements and how those feature sets are basically having impact on the the thing that you want to basically predict, right? Then the next step is basically formulating the problem statement with respect to what kind of algorithms do you essentially need to use, and what is going to give you the best performance after doing a lot of hyperparameter tuning. And then what you do is you basically take that trained model based on the first iteration and do something like A/B testing. So A/B testing is when you try to use the capability of that model for some set of user and not use it for other set of user. And then you try to understand that how by adding this feature or this model in my entire pipeline, how is it improving my metrics, and that's where validation and execute essentially comes into the picture, where we essentially try to determine of how these models are basically performing based on the data on which it was trained, and how is it performing it in real life, right? So these are very important different steps in building the entire data science pipeline, which needs to be given a lot of importance rather than just taking the data as it is and just using any algorithm and putting it on top of that and then quoting the metrics. So, like I said, one more thing to understand here is what are the different steps and what kind of an skill set is required, right? Obviously, you cannot have one engineer solving this completely end to end. right? Obviously, you need different skill set for each of these aspects to make you a successful to make this problem statement successful, right? So first is the exploration and model prototyping, and that's where a data scientist comes into the picture. And the role of this data scientist is to basically prototype on a subset or sample of data set that needs to quickly run couple of prototypings using multiple models, test the right feature set and the algorithm that's need to be chosen to get the best metrics, right? And here again the rapids ecosystem plays an important role because it helps you to basically do accelerated data wrangling, data visualization, as well as fitting these machine learning algorithms on large scale data sets and help and will give you the results much faster. So you as a user now, if you're working on large data, don't need to wait couple of hours for or probably even couple of days for the analysis to finish or for the model to complete, right? So that's where in the exploration and model prototyping phase, rapids becomes a very integral part for the data scientist in his toolkit arsenal. Now coming to the second point, that is how do I take it to production for training and evaluation stage, right? And at this stage, the ML engineer will basically scale up that model and apply it on the large data set, right? And this is where Dask plus Rapids comes into the picture, where now, say for example, when the data scientist was doing the prototyping on the smaller data, he must have just probably used a couple of GPUs. Now, when you want to do it for the if you want to train the model on the entire large scale data set, right, or on the full data set, at that point of time you need to understand how do I distribute this entire computing across multiple GPUs, not just within the system but even across the system, right? And that's where Dask will help you, because Dask is basically a distributed scheduler that will help you to break that large scale data frame of say million by million rows and columns and split these smaller chunks across all these computing blocks, again within the node and outside the node, and start doing the computation. So again, Rapids plus Dask becomes crucial for the production, training, and evaluation stage, right? And on the left side, where you basically need to do model scoring and inferencing, we have a library called Phil, and other compiler technology like TensorRT that helps you to take these models and optimize them on the hardware level so you get the maximum performance. And again, we'll talk in a very much detail and even during the hands-on tomorrow, that how do you optimize this in production as well using TensorRT and Triton. And for data science, it's basically the Phil library, right? So again, we have enough toolkits that can be used by data scientists to ML engineers and operation engineers to even data engineers that will make your life easy, right from the exploration and model prototyping to production, training, evaluation, and even to the production part, which is model scoring and inferencing. Right, so I've already talked a lot on this. Let's move more on the couple of more terminologies, and then I'll move to the rapids part of it. Right, so essentially what we see is just a second, yeah, there are two kind of processing that we see in today, right? One is called batch processing and second is called streaming processing. And what we see is in batch processing, what we want to do is we want to process large amount of data, right? And it is okay if you don't get the output at that very second, right? Or don't get it in real time, right? So what this processing, I mean, what happens in batch processing is you say that, okay, I want to compute it on this large scale data, and you put that job probably overnight, right? That's why it takes a couple of hours to a couple of days. And the focus is on high throughput rather than latency, right? And again, this is generally very important for ML training, right? Batch jobs are generally used for ML training workloads. Now, there is a second part, right, where the amount of data that is being sent is less, but the time in which the processing needs to happen needs to be as least as possible. Hence, it is more focused on low latency rather than high throughput, right? And again, in this case, you might not have the entire large scale data set, but you might have some micro batches of the data that is coming in, and you want to do the inferencing within some milliseconds. And again, one of the best example that I would like to share here for streaming processing is the work that we did with American Express, right? So, and again, that entire work is very close to me because I was personally involved in deploying that project. What we did was American Express essentially has these real-time fraud detection mechanism, but they wanted to use these deep neural network algorithms to essentially find the fraud detection in almost real time. And in their use case, when they first deployed it, they were getting an inferencing speed of about 150 milliseconds. And for a use case like theirs, where getting the insight within 1 to 2 millisecond is the SLA that they had to adhere to. That means if they had built a pipeline that would take 150 milliseconds, which seems less to us, but is still not enough for them to provide that insight, because that time window is very large. And hence, using the TensorRT and Triton, what we did was we essentially moved their entire pipeline on top of TensorRT and Triton, and they could essentially achieve almost real-time performance of about 1 to 2 milliseconds. I'll also share a blog and a GTC talk link post this session, wherein you can go and see how using our tools we were able to provide these enterprise customers with almost real-time streaming processing capability even for deep neural networks. So with this, let me move more on the rapids part, right? And let me take a little brief of how the distributed computing used to happen in the earlier days, right? And as you can see here, right, one of the words which we have heard the most, right, in the last 10 years is Hadoop, right? Which is basically what which used to be the de facto standard for doing big data management as well as big data engineering, right? Wherein what was being done is there were two important components. One was the MapReduce framework, and second is basically the HDFS, which is Hadoop file system, right? And what used to happen was users used to break their large scale computational problem and basically store that across smaller chunks across the disk across multiple such nodes, right? And generally how that pipeline used to look like was you first used to do the HDFS read, right, which is the Hadoop file system read. Then you do some query. Then to do ETL, you first had to write that on disk. Then you again had to read it, then perform the ETL, and then again write it back on disk. Now for ML training, again, you had to read it back, then apply ML training, right? So this was not a one unified process, right? You had to continuously read, apply the operation, write on disk, and again read, apply the operation, and write on disk, right? So it was a very not a very efficient way of processing large data set on Hadoop. And that's where what happened was that the Spark in-memory processing came into the picture, wherein what Spark said was rather than reading the data, doing the processing, and then writing it, how about I take that entire data that I want to use for analysis and keep it in memory. So when I say keep it in memory, that means I need to keep it in the RAM itself, right? That means what is happening is you take the data, you feed it on the RAM, right? You load all that data in the Spark in memory blocks in the RAM. You do the querying, ETL, and ML training, all these three steps together, rather than writing the data back, reading it back, and then performing ETL, so on and so forth, right? So all these three operations could now be done together in one particular go, by having all the data in memory, right? And it gave us about 25 to 100x improve in performance, with less amount of code, more language flexibility, and primarily in memory computation. Now, what we did was that we moved to the next step where we wanted to now, shorten the cycles of these queries, ETL and ML training from CPU to GPU. So if you look at a traditional GPU processing, what used to happen was we used to first do HDFS read, then when you say HDFS read, basically you're reading it on the RAM. Then you basically read it on the GPU. That means you move that data to the GPU, do the querying, write the data back on the CPU, right? Then again read it back in the GPU memory, do ETL, so on and so forth, right? Which again brought us a lot of problem that we used to see in the first pipeline. So how do I address all these GPU reads and writes? Can I basically, apply similar paradigms of Spark in memory processing to essentially improve this? Right. So again, this is the same pictorial diagram, but just with some memory copies involved here, where basically you have application A, you are basically now trying to load the data here, right, onto the GPU memory, do some processing, get the output, put it back on the CPU, again convert it to the second application, again copy it back to the GPU, do the processing, and then again read it back, right? So it was a very cumbersome process, and basically it, even with GPU computing in picture, it took away all the benefits of the speed up that one could get. So what we did was we tried to remove these continuous copies across CPU and GPU, and that's where the Apache Arrow learnings came from, right? So so let me give an idea about what I mean by moving it across different applications. So if you see on the left side, in these ecosystem, there are a lot of different components of big data ecosystem, right? From Spark, then we have Pandas, then we have Drill, and then we have Impala, and we have different memory formats in which the data could be residing, right? It can be in Parquet format, it can be in Kudu format, it can be in a Cassandra database, or it can be in an edge-based database as well, right? And each of these systems had their own internal memory format, right? It was not one unified memory layout altogether. So what was happening was, if I had to move across these systems or software stacks, I had to continuously do the copy and convert. That means I had to read the data, do the computation, do the serialization, deserialization, and then basically it can be used by the other system, right? Or the another application. But with Apache Arrow, what essentially happened was, rather than doing all these internal conversions, which were wasting a lot of compute cycles, what if I can have one memory layout that can cater to all of these data, I mean, all these applications, right? And again, that's where the Arrow memory came into the picture. And again, Arrow is a very important memory standards in the Apache ecosystem, and is a very successful project. And even Rapids is built on top of this Arrow memory layout. So what it does is, it basically saves the data, right, in an columnar fashion. Previously, all the data used to be stored in a row serialized fashion, right? But in this case, we are essentially saving it in the column format, right? That means we are saving data in a columnar fashion. So basically, it helps us in a lot of reducing the overall overheads, as well as all these different systems can essentially refer to that same memory format, rather than doing the copy and convert, or serializing and deserializing. So with Apache Arrow, all that hassle of read and write across CPU and GPU got removed, and we again saw about 50 to 100x improvement in the overall process. So now, very similar to the Spark in-memory processing, we can now just do a Arrow read, do the querying, ETL, and ML training in one single pipeline without moving the data from GPU to CPU and then bringing back to the CPU. Sorry, bringing it back to the GPU to do these process. So now all of this can happen in one go, and you as a user don't have to do a lot of memory transfers across all these pipelines. So with that, I'll talk about the Rapids core, which is the focus for today. So we have an open source data science ecosystem, and good part is, right, everything is in Python API, right? So every user who has used Pandas, Scikit Learn, NetworkX, Matplotlib, now you don't have to learn any part of Cuda, or don't need to know about Cuda programming, right? You can still use a very similar API looking structure and still be able to move all these workloads on top of GPUs, right? So Pandas is generally used for data wrangling and data analytics, right? That means you want to take a data frame, you want to apply group by operation, or you want to probably sum a particular column, or probably you want to do some rolling operations on top of that. All of that can be taken care by Pandas. Scikit-learn is used for importing a lot of these machine learning algorithms from the library itself. So you as a user don't have to, implement it from scratch. And then we have Network X for similar purposes for graph analytics, and then we have Matplotlib. I'm not going to talk about PyTorch TensorFlow today because that is more on the deep learning side of the story, which we'll talk about in more detail tomorrow. And then you have this Dask scheduler that helps you to scale your data analytics as well as the machine learning pipeline across multi GP across the system, right? That means across multiple CPU cores and even across multiple CPU based systems as well. Now with Rapids, you can essentially you're getting the goodness of each of those APIs or the application frameworks like Pandas, Scikit-learn, and NetworkX and Matplotlib just with the GPU accelerated version of it, right? Which we call it as cuDF, cuIO, cuML, cuGraph, cuXFilter, and Plotly, right? And again, good part is you don't need to know anything about CUDA at all, right? Sure, some fundamentals, but you don't need to know about CUDA programming and CUDA C to basically move all of this on top of the GPUs, right? So we have already done all the hard work, and you as a user can focus more on solving the business problem rather than building these algorithms from scratch and building it highly efficiently on GPUs. So this is the entire ecosystem that I talked about, and let's get into more details about this. So first, let's start with the ETL part where cuDF and cuIO is involved, right? And ETL again is the backbone of all the data science work, right? Machine learning is probably one important component, but most of the time of a data scientist or an ML engineer goes in data wrangling and getting the data in the right format, right? So let's look at the productivity of a data scientist in general, right? So on the left is a CPU powered workflow, right? So generally say, there would the data scientist would come in, he'll configure his ETL workflow. He'll probably, start the after configuring the ETL workflow, he'll probably run that workflow, which has gone for some computation. He'll try to get some coffee till 12 or 1 o'clock, right? And then he realizes that, hey, you know what, maybe I forgot one of the important feature. Hey, let me go back and reset that ETL workflow again, right? And then he'll go back, he'll do that changes again, and then again it will take a couple of time to basically run that workflow. And again, just to find out that maybe, hey, he has missed out something again, right? And the entire day goes in this, right? And you see that there's a huge time that is required for running these ETL workflows. Now with GPU powered workflows, what is happening is now the time taken for running these workflows have been reduced so much that you can essentially within that same stipulated amount of time, you can do multiple experiments and you can keep swapping and including different feature set based on the performance that you're getting, right? So essentially this increases the overall productivity of a data scientist in terms of running multiple experiments and multiple workflows within the same amount of time compared to a CPU powered workflow. Now, let's look at the ETL technology stack, right? Like, what are the different layers involved and what NVIDIA has worked on and what you as a user needs to keep put focus on, right? So as you can see, everything is built on the underlying CUDA library. On top of this, we have our CUDA stack called Thrust, Cub, and Justify, right? So these are some of the CUDA based libraries that are essential to perform a lot of these ETL functionalities, right? So all of the base functions for group by, sorting, summation, all of those logics is written in all of these libraries like thrust, cub, and justify. And what we have done is we have tried to provide a front end using C++, coding the cuDF C++, which essentially provides the user to run these GPU accelerated cuDF on a C++ application framework as well. But like I said, right, if you are a Python user, you don't want to know about C++ and CUDA. you can essentially still stick with the Python ecosystem. And that's why we have the Python bindings, wherein we are basically binding these C++ functions directly inside the Python API calls, right? And so you as a user don't need to learn any new APIs. You can still use the same APIs that you have learned in Pandas and Scikit-learn and reuse them even to run it on top of GPUs using cuDF and Dask cuDF. So here are some numbers to support that. And again, when we do the practicals, I'll show that in much more details of how much improvement in performance is happening. So on the right side, you see that for writing write function and the read function, right from reading from Parquet format to CSV to ORC to even JSON, we see that there is a pretty good performance that the cuDF brings onto the picture, right? Obviously, for JSON, we are still trying to improve the performance, but at least for Parquet, CSV, and ORC format, we see that the read happens much faster, right? And similarly for the write function as well, right? And this is based on a data set called New York Taxi dataset, on which these benchmarkings were done. Now, looking at the cuML part, right? Basically, cuML is our GPU accelerated library for machine learning, or a replacement for scikit-learn. So let's look at the API, right? So this is basically a sklearn based API for basically importing a data set like make moon, right? And then applying pandas data frame on top of this, right? And on the right side, we are applying a clustering algorithm like DBS scan on top of this. So you see the API over here, right? That means I'm simply doing DB scan and then I'm putting some hyperparameters and then I'm calling a fit function and then I'm calling a predict function to basically get all the predictions over here. Now let's look at the GPU version of this, right? I simply replaced the pandas with cuDF over here, right? That is the only change that I had to do. And on the cuML part, that is on the sklearn part, I just replaced sklearn with cuML, right? All the API that is of fit, predict, right? All of that remains the same. So you as a user who are used to pandas and scikit-learn now don't have to learn any new API and can still sit and still use the same API and now move your workloads on top of GPU. So we have tried to make very similar APIs for each of these frameworks so that you as a user don't have to go through the hassle of going through the documentation and finding the right API for running your workload on top of Rapids. Now there are different GPU accelerated pipelines available for machine learning, right from classification regression tasks for decision tree, random forest, logistic regression, k nearest neighbor, SVM, naive Bayes, to other algorithms as well. Then we also have GPU accelerated pre-processing like text vectorization, TF-IDF, count, target encoding, cross-validation, and a couple of clustering and decomposition algorithms like Testney, spectral embedding, k-means, DBS scan, so on and so forth, right? So all of these we keep on adding more and more algorithms to the cuML stack so that you as a user can essentially use them for any of the machine learning algorithms that you essentially want to use. And this is the ML technology stack. Again, looks very similar to cuDF, but here what we have done is we have added some couple of more components. That means in terms of the libraries, now we use Thrust, Cup, cuSolver, nvgraph, cuClass, cuSparse, cuRandom, and cuBlast as the underlying CUDA X libraries. And on top of that, we have few cuML primitives, and then we have the cuML algorithms being implemented on top, right? And then for these algorithms to run in the Python ecosystem, we have the Python bindings as well. So with that, I think in the hands-on part, I'll be covering NGC containers and I'll be covering Rapids in core detail. That means using cuDF, using cuML, and third is using Dask along with cuDF and cuML for doing large-scale data analytics. As well as I'll show you how do you set up your software environment. That means how do you essentially set up your environment with all the libraries rather than you trying to install it hand by yourself each of the components, right from the CUDA library to the Rapids library, and all the other required ecosystem packages that are there, right? So all of that can be tackled using the NGC containers, and this is the much larger view of how we have built the entire software infrastructure for machine learning, deep learning, and data science. And we're just going to look at one small piece of this in today's session. Tomorrow we'll look at the deep learning component, which is the CUDA X for AI for Triton, TensorRT, Nickel, cuDNN, and cuBLAST, DALI, and look at more specific frameworks like PyTorch and TensorFlow in detail, right? But even apart from that, we have industry-specific SDKs for healthcare, video analytics, conversational AI, and others, which we essentially want to also, have, future workshops for, so that you as a user who are working in these domains can leverage these software platforms for efficiently building your pipelines on top of the GPU infrastructure. So with that, I think we have almost reached 12:15. I'd like to, take a pause here and basically, hand over the baton to Professor Pabitra